It is definitely, it probably might have been from the turn of your turn.
Yeah, it's gone.
Secretary's always got my back.
There you go.
You got 2 things to stamp, 1 warm-up to do, and then take out number 7.3. No, 4, 7.4.
Well, at least
We're stamping the energy use inventory and also 7.6.
this is a bad notebook.
This energy use inventory.
7.6 is the movie question that you did in class like a month ago. You'll be fine.
My energy thing? How's that, dude?
Okay, you should probably get, hold on to DJ. Page Friday. Friday, 2, 7.6. Yeah, so not this.
Yes, sir. Oh,
This.
I'll look for the
Let's go find it.
for the 7.6.
The energy use inventory is yellow. Okay, well, I guess I'll snap it because, whatever. Yellow. There you go.
Gotta find it, don't worry.
I don't know what I'm
Come back to it.
Oh, there we go. Alright, do all that. Yeah, they're back there.
We're actually missing from my bill, so just great.
I don't want to stand the word sports.
Well, let's see.
You can burn it. You can retain the heat that.
Yeah, you're right.
All right, now me. I'm glad you had that moment. Who's on it? Who took a picture of me?
It's on the tweet, team tweet. It's you on the bus going to the
Oh. What if nobody can tell it's me?
Except everybody.
Everyone. Yeah.
Wasn't that like 6 months ago?
Sorry.
Yeah, who did that, by the way? Somebody's going to pay. Who? Yes, but this is not anonymous. Who did
I remember
that?
who tweeted it, but I don't remember. I just remember seeing it, but I don't remember who tweeted it. Wait, what? It's
Sue him, Jose.
Wait, what is it? Can we see?
This will become personal. Heads are going to roll.
It's not even.
Yeah, right. You can't tell.
If it wasn't colored,
And no Jose.
Wait, Jose, you're where Forrester has like a this big photo of you on his wall?
yeah, it's like when you
You and your wife have a bunch of candles next to it and like
It's
crazy.
It is. It just.
Me and my wife?
Yeah.
So.
What? It's like something dropped. It's like it's like you walk in, you see the You're like
He's trying to steal your wife.
so weird.
It's like a selfie.
You guys are
Cool.
I'm trying to find it.
All right. All right. A couple of quick things while Homeboy's stamping. I guess everybody liked their crazy sub?
Yeah. So cute.
Great. On Wednesday afternoon, my daughter tested positive for strep throat. So we had to, she's fine. We had to start her on antibiotics, and she's not allowed, or she should not be going back to school for 24 hours. So yesterday I stayed home with a kid that wasn't sick at all. So we just sort of like did a couple of art projects and watched a little Netflix, then we went to the climbing gym, and it was like a really nice day.
Why did you get tested for strep throat?
So our whole house has been sick since like December. And then my boy had a positive strep test like a week ago. And they were like, we should probably check her too. So they like, she had the first test was inconclusive, so they needed a second type of test, and that one took longer. So everybody's good, and like everybody's feeling fine. And then the test came back, and so we still have to treat her for it. She's around other kids. And so I had an easy day off. Sorry I couldn't be here though. It was totally last minute. Usually I videotape myself lecturing to you. But I found out I had to stay home on Thursday when I had already started my Wednesday babysitting my son. So I didn't really have an opportunity to set up for Thursday. And so I hope that you guys had a chance to make your day useful. I heard from my first period class that it took a long time to copy the content of the board, so I'm glad that could help. And then, how many of you actually made progress on the solar house modeling? Well, planning, yeah. So I'd like to offer some answers about that. I'd like to offer some answers about that. Does anybody need any help designing or preparing their plans? Are there any questions about what I expect from you? Everybody knows there's 3 separate papers, what goes on each of them. Yeah.
Can we see some examples?
They're in the drawer in the back. You can check them out later. It's labeled solar house plans.
So for the layout, I know you're not supposed to show like the interior, but what if you have something like for convection, you have like something parallel to the wall? How do you want us to show
It's not
that?
here.
Like say
Wait,
like
no.
interiors like
Explain.
I'm going to change the plans next year. I know where you're going with this. Everybody should hear this answer. You do not need to show interior walls unless they are part of your passive solar design. So I don't really care where the bathroom is, but if the walls are funneling air upstairs, then you'll need to show the ones that are involved in that cycle. So in one of the cross sections or one of the above views, you would show where the wall is and how tall it is, for example.
so like if you have glue on top, for example, and if you have like a pipe full of like with hot water, you want to show the pipe, or does you have
No, but remember that circulating water is not passive. Yeah. One is a three-dimensional color street view poster size. The other one's a black and white construction schematic of all the different views of the house. So front, side, other side, top. Usually at least 4 or 5. And it's listed on the thing.
Do we need 2 different size poster papers?
They don't have to be different size, but those are both poster papers. And the third sheet of paper is a detached key that has the numbered innovations and how they work in your home.
How much information do you want for each?
Just a blurb to prove you understand the concept. Less is better. Yeah.
How many pages can it be?
If it's more than a page, you probably wrote too much. What else? I don't obsess over size. Like this whole thing about like how many pages and stuff. Like, but I think if it's more than a page, you're probably like you could make it shorter. Are there any energy use calculations you'd like to discuss? Because this will definitely be on the AP test, I will probably have to ask you questions like this somewhere else in your education. Is there anything I can help you with on these types of questions, or are you ready to do it? Yeah.
I like the energy use of appliances, like kind of like the figuring out like the month and year, like.
So you've got some numbers, right?
Yeah.
Give me a wattage of an appliance.
Okay. TV 160 watts.
160 watts.
Yeah. And I just said like 93 hours.
93 hours a month?
Yeah.
So let's start with 3 hours a day. Everybody should hopefully follow. Paul, 160 times 3 is 480 watt hours per day. That's the same as 0.48 kilowatt hours per day. Agreed so far?
Yeah.
And if we had 30 days, then that would be something. 30 days would be what? 14. Anybody want to save me from the embarrassment of not doing math well?
We'll just watch you.
Multiply by 30. So 14.4?
Yeah.
Okay. Watch. 14.4 kilowatt hours per month. How much do you pay for electricity at your house on average? Should be on your paper. On your worksheet, I mean. There was a question on the first side at the top.
Just pay it for like 1 minute.
That number. What is it? Lexi, tell me.
0.19.
0.19, okay. So watch. 0.48 at 0.19 dollars per kilowatt, right, is roughly 23 cents per day. And this at 19 cents per kilowatt hour is, I'm just going to rough draft this number. It's about 14 times 2 is about $22.70 per month. Because I keep the dollars per, like this is dollars per kilowatt hour, so the kilowatt hours cancel out, and I've got dollars on top and months on the bottom.
I get that.
That'll make sense to you? Would anybody like me to do that again? I'm happy to. If not, I'm going to move on and it's good on your test, so we're good?
Could you do one more?
What?
Could you do one more?
No. Numbers.
Oh, I just have a question.
Uh-huh.
On here it says like the conversions for some of them. Will we have to know those, or will they be given? No.
You got a number?
441 watts.
What?
Do 441 watts on TV.
You got 441 watt television? And how many hours do you use that device?
I said 60 per month.
So 2 hours a day. Right? Because I'm multiplying the units, that is 882 watt hours. I'm multiplying the units and just adding them per day. Do you agree with that? And do you realize that that's 0.882 kilowatt?
And then you multiply that by 30.
Does that make sense how I made it into kilowatts?
Yeah.
Girls, bye. And then at your house, what does a kilowatt cost?
26 cents.
So at your place, it's $26 per kilowatt hour, right?
Yeah.
And my kilowatt hours cross off top and bottom, and I'm left with dollars per day, right? Dollar on top, day on the bottom. And 0.882 times 0.26 is probably, I don't know, 23 cents a day. Is that right?
Yeah. What do you say for the first box? Like the amount of hours? Oh wait.
What?
The amount of
The
energy
number?
it consumes.
The amount of energy it consumes is 441 watts.
Oh, okay.
And then per day, it consumes 0.882 kilowatt hours per day. How many of you am I not helping with this? Like, didn't get it before, don't get it now? Everybody's got this? I don't believe it. People just aren't asking me any questions. If you ask, I can help you, but I don't know how to just give you content without you asking me where the...
You don't need to know this for the test?
You absolutely must. This will be tested for the 100th time.
Sorry.
How can I help? Yes.
Like, on the test, how would they, like, propose a question?
Like that?
So they would give you an appliance and its usage and then ask you for...
Yeah. How much it costs per, yeah. For example, at a place where you spend 21 cents per kilowatt hour, if you watch TV 3 hours a day and your television has this efficiency, how much are you spending per month? Seems like a reasonable question. Yeah.
Is the 0.26 like
Word problem, okay.
one of these, or where do you find?
So it was the first question that you answered on your paper on the front page at the top. Where that's your cost per that.
Cost of electricity.
Oh, okay, I see.
That's how many dollars you pay per kilowatt.
Okay.
Yeah.
When you get the 0.882 kilowatt hours per day, do you multiply that by how much cents it is?
Yeah, how much you pay for each of those.
So 0.882. Oh, I mean,
I-
times 30
That would be in a month.
for a month.
Like
$26 for a month. Is that?
$26 a month. I think that we may be off somewhere a little bit.
I did.
It's okay. But slow down a minute. I want everybody to notice something. The units mean something. This is not arbitrary. These are words you can speak in English to convey content. This is not jargon. These are like concepts that mean something. A unit of energy and a unit of time. Kilowatt hours per day is how much electricity in a day. And then the dollars per kilowatt, that's how much you're spending per unit of energy. So, how much you're spending per unit of energy and how much unit you're using per day. In other words, how much you're spending per day for the energy that you're using. If somebody could please take out a calculator now. Thank you. What is 0.882 times 0.26, Paul? 0.882 times 0.26.
0.229.
About 0.23? Great. So at your house, I want you to see what I'm doing, because this is what I would have answered if I had your paper, Mackenzie. This is the appliance. This is how much you use it. So this is how much energy you use to operate it every day. And watt hours is not a very common unit, so I added the decimals to make it into kilowatt hours. Okay? Now that is your energy usage per day, and this is your cost per energy usage. So when I multiply that, I can cancel out the kilowatt hour, then I'm left with dollars on top, and day on the bottom, dollar per day. And so that's how much we're spending, 23 a day. And then in a month, there's how many, right? So you could multiply that by 30 day per month, day on top, day on bottom, cancel out. We're left with dollar on top and month on the bottom. And 30 times 0.23 is what? 6?
It's 6.9, but
Okay.
I got
$6.9 a month.
and I got 7 in the beginning, so I think I calculated it differently, but got the same number.
Yeah, so you can probably multiply this into a month first, and then multiply that month by 30.
Because I think I originally
Or multiply that month by your
multiplied
cost.
0.441 kilowatt hours times 60.
Right, so that's where you included your 30. That makes sense. Yeah. Yeah. So you're still arriving at the right thing. You've got all the concepts. You just went in a different order. There's no single way to answer that. There's a lot of conversions that we do. Yeah, that's cool. If anybody wants to ask me a question, I really want to help with this, but like I can't communicate without the question. Like we were able to agree on something, I think, right? Because this made sense to you. You're confident. No question? Okay. I would like to finish our renewable energy stuff. Did we talk about hydrogen fuel cells last time?
No.
Did we talk about solar energy last time?
Yes.
We're going to have to move very quickly today. We start with number 30. I'll remind you, what's written on the board is what I need to remember what I'm going to say. Most of you will probably need more notes. First, label the parts of the fuel cell on your paper. You need a metal layer, a semi-permeable electrolyte membrane, for positive charges to go right. Please look up. This is an important detail. Right there, my index finger. Positive charges going right, that makes a difference. Then a metal on this side, coated in a catalyst. Who knows what a catalyst is?
A reaction. No, it speeds up the reaction.
Speeds up or starts a reaction. What?
That's the purple dot?
That's the purple dots. They are the catalyst. Something that speeds up a reaction. It makes something happen. Chemistry is started by these. You should know that the catalyst is usually, please look up, platinum, and that platinum is expensive. You could ask Lil Wayne. He's got $1 million of platinum in his mouth. $1 million grill.
Nice.
Yeah, I think it's very nice. You guys know that when he went to prison for a year, the state had to pay the dentist to take out his platinum caps because he argued that that would be inhumane to be beat up in the prison yard so that people could steal his teeth to buy cigarettes. And so the state had to pay to get him ceramic caps to replace his grill. And then when he was released, the state had to pay the dentist to put his grill back in. It's like a part of his career.
Nice.
Is that not the most absurd thing in the world? What? Cathode is a metal that charges positive, and anode is a metal that charges negative.
Kill. Wait, cathode does what, and anode does what?
So maybe it was a mistake to bring up Lil Wayne. Here we go. A metal that charges positive on this side is called cathode. And on the other side, because the other metal charges negative, that's called an anode. So I'll review the 4 parts. The catalyst, which is usually platinum, it's usually very expensive. That's the problem with hydrogen fuel cells. The catalyst is expensive. That's an obstacle. Anode is the metal that charges negative. The semi-permeable electrolyte membrane in the middle is positive going that way. And cathode is on the right. Hydrogen's a very special thing. Does anybody know the 3 parts of the atom? There's a thing, a thing, a thing. They are?
The proton, neutron, and electron.
Proton, neutron, electron. Everybody know that? Proton, neutron, electron. The charge of a proton is positive. A neutron is neutral. And electron is negative. Now, all atoms have these 3 parts, except for, this is the big deal, hydrogen. Hydrogen does not have neutrons. Hydrogen, this is a big whoop, is just a proton and an electron. That has to be in your notes, just a proton and an electron. There are only 2 parts in hydrogen, just a proton, just an electron. So now, please look up. When you put hydrogen on the catalyst, the hydrogen will split. What are those 2 parts again? Proton and electron, right? Now, what charge does a proton have? Positive. And what type of electrolyte membrane do we have? And so what's going to happen to those protons? Where will they go? That way. Please look up. This should all be in your notes, but you have to know what I'm talking about. Hydrogen splits into electron and proton. Protons are positive, so in this membrane, they go, look here, that way. That gives you a bunch of electrons on this side and a bunch of protons on that side. In other words, we've charged the battery. Negative on the anode side, positive on the cathode side. And now we can connect them with a wire and the electricity will do work. On the other side, when those electrons and protons get back together, they grab some oxygen out of the atmosphere to make water. That's not balanced, obviously. A hydrogen fuel cell is not an energy source. We think of hydrogen as energy storage. I drew that on my diagram here because look, it takes energy and a lengthy process to make the hydrogen. Once you have hydrogen, sure, you can feed it to the device and make electricity. But it takes an input of energy to make the hydrogen. So this is not a source. It's just storage. The hydrogen is a place to put energy. Because you spend energy to make it, and then now that you've got the hydrogen, sure, you can get energy out of it later. Contrary to popular belief, these are not explosive. It's a different kind of hydrogen process. This is not a bomb. And keep in mind that this usually takes quite a bit of work. It's not efficient. If you use 100 units of electricity, you might get 10 or 15 coming out of the fuel cell. It takes a lot of electricity to make the hydrogen in the first place. Anybody have any questions for me about hydrogen fuel cells? Yeah?
How did the electrons get to the right side?
Technically, they're not going anywhere. It's just a proxy for. It's easier to explain it this way, but their excitement level travels through. So it's basically the current going. Anybody else? Next. Hydroelectric is a very, very simple explanation. I'm guessing everybody here, as a child, threw rocks into a stream to make a pool. Has everybody dammed a creek or a stream as a child? They just pile up rocks to make a little pool in a creek or a stream. Sarah was locked up for most of her youth.
No, we aren't monsters.
Right, so most children, if they grew up with any access to creeks, have tried to plug them. The concept is the same. Maybe you've seen it somewhere, like pools up at Rattlesnake or whatever. Please look up. A dam is just blocking a river. So when you block a river, it creates a reservoir of water. That's what dams do. They block a river to trap water. And now that you've trapped water, you're ready to make electricity. Please look up. If you open the reservoir, water comes through, and because it's coming under a lot of pressure, it'll spin a turbine to make energy. This is relatively renewable because the baby Jesus keeps making rain. This is somewhat sustainable because at least it doesn't cause CO2 emissions. Unfortunately, as we'll learn in a later unit, these don't last very long. Reservoirs fill up with sediment in many places under 100 years. And there are other challenges to damming rivers. We'll talk about that in the water unit. Anybody want to ask me anything about hydroelectric power?
Is it used in electricity?
What?
Does it use electricity?
Yes. Next, number 33, I'm going to go out of order. Let's talk about the wind really quickly. A wind turbine is literally an electrical turbine held up in the wind so the wind will spin the blades. This is the simplest thing. You all remember the slideshow about turbines, right? You take a turbine, you hold it in the air, and the magnets are moving. It's a piece of cake. There's a lot of good news. For one thing, this is the fastest growing energy source on the planet. For another thing, it's relatively cheap in the dollars you got to spend to get electricity out of it. It's actually a very cheap method of energy generation. Also, we have they use a lot of land, which is kind of a bummer, but we have a lot of land, especially on the sea bottom. Most new wind projects are in shallow coastal water. They're anchored to the sea floor, but they stick out above the surface. There's a lot of politics and logistics to putting these on land. But putting them in shallow coastal shelf areas, that's actually pretty doable. And the one downside to wind turbines is they're basically a blender with the lid off. They kill a lot of stuff. I had to walk through a wind field once, And it looked. Has anybody ever been hunting birds or seen bird hunting? Like, when you shoot birds, there's like feathers everywhere. You know, you can tell if you hit the bird because it's like a feather bomb. And if you walk through a wind field, it's pretty much like that. Like people got in a pillow fight, basically. Like it's just a field of feathers and dead birds.
It's pretty bad.
My wife and I walked through a wind turbine, a field of wind turbines, and she didn't make it. That's my first wife. I made her go first. When my wife and I walked through a field of turbines, the number of dead birds on the ground was pretty memorable. And apparently, there's like a big pressure differential between the front of the blades and the back of the blades. Because the wind is striking something, there's a lot of air molecules on the front side, not very many on the back side. So when birds, and especially bats, fly around or between the blades, as they come through, the pressure drop will pull their lungs out of their mouth. And so even if they don't have the actual lung hanging from their open mouth, it does like cause their lungs to bleed and they choke. And anyway, these things are really deadly. So the funny thing that erupted a few years ago is basically this battle between one group of environmentalists and a different group of environmentalists. Exactly. There's all like the energy enviros versus all of the diversity enviros. And so you've got people saying, but you're killing all the beautiful birds, and somebody else is like, but we're saving the planet from climate change. And it made like for a pretty interesting battle within the environmental movement. As it turns out, you can scare away wildlife. So people have used like lights that kind of work at night sometimes, and they've used like basically a kazoo is like a really fancy sort of kazoo. So it's like a reed instrument. If you guys know what like the woodwinds are, like it's like a little wooden reed, like a bamboo piece that just vibrates and makes like an unpleasant sound. Of course, that's not really popular with the neighbors because you've got like 1,000 kazoos going all night.
This will make the best year.
But it's been an interesting process of development. In every area, you have to use a different combination of exclusion devices to keep the birds and the bats from getting slammed. It's unfortunate, but the exact places where you put a turbine, where it's really windy, that's also where the birds like to fly. I mean, pretty much, if you see where all the birds are going, that's where you want to put the turbine. So there is like a really, it is an honest conflict. This is not like a simple solution. First, second, third.
Like, you know how fans have like that little cover? Can you just do that for it?
Kind of, but the logistics and cost of that is not realistic for these. The best turbines now are huge, and so I think it's just not a practical. Plus, it blocks a lot of wind.
What if it's like metal? Like just go straight through.
Blocks a lot of wind. Yeah. Yeah.
That dies, that's the simple.
Yeah.
At least for like bats and stuff, couldn't you just do like some type of like cheap sonar type of like thing that's just like really loud for them or something and just like don't come this way?
Yeah, so one way or another, something that makes noise. I don't know if sonar or what, but yeah, they're either land-based or they're on the wings themselves. Then there's other trade-offs, like the efficiency of the device goes down, and your neighbors complain, so that's been like that's the current status. Anybody else?
So is the effect of like the pressure differential so drastic on them because they're smaller than us, or would the same thing happen?
I think it'd be pretty bad if you were right behind it. Like it's spatial, and it's not always like if you kind of got to get the bad luck of being in the sweet spot. You know, like if the blade was right down behind you, then.
Okay.
All right. Number 32, the tidal power stuff. please look up. There are 1, 2, 3, 4 main options. You'll notice a pattern. 1, 2, and 3, not really viable. So these were experimented with. A few of them have been constructed, and it turns out 1, 2, and 3, they're just not doable for a number of reasons. I'll explain what's up, and then I'll try to explain what's wrong. I'm glad you already copied these yesterday. Number 1 is called tidal barrage. And you can imagine a bay like San Francisco Bay. You know what I mean? Where there's like water surrounded by land. And you build a dam across the opening. So imagine if the Golden Gate Bridge was a dam. Okay? Now I'm going to explain how this works, but you'll have to watch the visual. If I keep the dam closed until high tide, I'll have a lot of water in the ocean, but the level of the bay will be low. I open the valve and the ocean rushes in to fill the bay all at once, and that can spin a turbine. At that moment when I filled the bay, I close and wait, and then I'll have a bay at high tide, but when the ocean's at low tide, I can open that valve and the bay will drain all at once to spin the turbine. Does everybody understand what I mean about that differential between bay tide and ocean tide? When the ocean is high and the bay is empty, you spin a turbine by letting the ocean in, and then you close it. Wait until low tide, and then you let the bay drain all at once, and then that spins a turbine again. Questions?
Isn't that a dam?
It's a dam. Yes, but it's an ocean. It's a dam for tides. You're damming the tide. Yeah.
So what happens to all the marine life in the ocean and the bay?
That's one very big part of this problem. That to make these things, like there's no way to make this omelet without cracking some eggs. That's been one of the big problems. And by the way, it's not just any ocean life. Bays are the most critical parts of the ocean interface because that's basically where fresh waters and salt waters meet. You can imagine the salmon and stuff, like that's what they would go through. Yeah.
So like certain times of the month, the tides aren't as like extreme differences as others. So like would that work when it doesn't change?
Not only certain times of the month, like you guys know that we have the big tides, the full moon and the new moon, but very little tidal variation 2 weeks later. So during the low tide parts of the day, like right now, the difference between high tide and low tide is 1.5 feet today. So that doesn't give you a lot of power, right? That's one problem. Also, there are no tides in the temperate parts of the world. This only works at the extreme north and the extreme south, where you've always got tidal variation. This does not work in the tropics or the temperate regions where most people live, because you only get a few big hits of electricity a month. Good news is I can plan the high tide and low tide 20 years from now. So I can tell you how much electricity I could make. You can schedule this. But it's only usable in the extreme north and south, and it takes a lot of money to build and maintain these over time because saltwater and sea life make them very, very difficult. As far as I know, 3 or 4 of these were built. None of them was profitable. They tried it in Argentina, Scandinavia, New Zealand, and another one that I can't remember, I think Alaska or Canada or something, and none of them lasted very long. Anybody have any other questions about number 1, the tidal barrage? Yeah?
So where's the energy coming from in this system?
Basically gravity.
Like, how does that work?
What's your question?
So there's like, how does gravity make energy? Like, obviously there's some form of entropy going on.
Yeah, there must be some heat and resistance, but you imagine that when this water is spilling into here, it'll accelerate until their level, right? So that's what spins the turbine, is that differential water pressure, because water wants to level itself.
So does the moon causing the tide to rise, like, does it like slow it down?
Move far away.
Does this slow the moon?
Like, yeah. It's
No,
like,
there's no feedback to this. So you're regionally preventing the tide from occurring and then letting it happen later. This would be happening in nature anyway inside the bay as a gradual daily 12-hour cycle. And instead of letting it happen one way, you're just letting that energy build up and then you're flushing it through the turbine all at once. I think I get your question, like what's the feedback? Like how does this like take energy out of the ocean somewhere? Is that?
Yeah.
But yeah, you're just slowing something that's happening anyway. So that would be like catching all the snow in an umbrella and then closing the umbrella and letting all that snow fall at once. That'll be heavier, right, than the snow pitter patter. That's going to be like a big dumping of snow all at once from your umbrella. You're just using one mechanical way to prevent it, and then you pull the trigger and then it all happens at once. Like snow on an umbrella. Yes, you make okay? You still don't like this? Ask your question. I don't know how to say this.
I mean, I don't know. It's just sort of been like something I've always wondered is like, how does gravity make energy? Like ever? There's obviously entropy in all systems, but where's the entropy in gravity?
Good question. I mean,
maybe
maybe there's a very small amount of water friction that's making heat like against the air or against the land. I don't know, man. I'm not like trying to argue. I don't know that I can answer that part. Like, I don't know where you would find the entropy that you can measure in that system. I guess maybe you could argue that the moon's being sucked into the Earth.
No, it's going further away.
Oh, it's getting away. Okay, so maybe this is slowing the escape of the moon from the Earth or something. I don't know. I mean, gravity is kind of an impossible thing, and isn't that sort of like a crux point in astrophysics? Nobody understands the cause of gravity.
Well, I mean, yeah, but we understand entropy, so. I mean, we know that there should be entropy in somewhere in the system, and I'm just like trying to understand where it is. So yeah, I mean, if you don't know, that's fine. I don't know too many people who do know. So.
Yeah, I don't know. It's a good question. Number 2, you can put a turbine under the water and let the moving water spin it. You know, there's places that have like really strong bottom current. Like where coastal waters spill off the continental shelf into deeper waters. So you can capture that current and use that water movement to spin a turbine. But apparently the efficiencies underwater are very, very different. It takes kind of a ton of water movement to barely spin a turbine. So please look up. People have tried this a number of ways, and we can barely get them to operate. They're fragile, and they don't really seem to produce a lot of energy as far as we can tell. We haven't found enough current that's reliable to make a significant amount of electricity. Yeah?
Wouldn't they break easy if, like, fish or, like, seaweed and stuff?
Probably. All of these are scary because working in the ocean with moving parts is really, really, really challenging. Anybody who owns a boat will tell you salt is the enemy of all engineering. So, like, it's very, very difficult to make these long-lasting. Apparently, there's been more success, please look up, with tidal reefs, which are the turbine horizontal. So in shallow water, like coastal water, like the stuff that comes spilling off the slope right at the wave pulling back. Problem here is, of course, these are fragile habitats and the same high maintenance, and obviously that's a place where you want to not have stuff like right in the intertidal. So this was another concept that people have tried, didn't look that good. Both of these are ideas that for a variety of reasons are not really being pursued as far as I know in large scale anywhere. Number 3 is another idea that's not going too fast. Please look up. It's called ocean thermal. And it only works in tropical oceans where the water's really hot. Is 85 degrees enough to boil water? No, not water. Baylor's looking it up. Thanks. Appreciate you doing this.
Mercury.
Yeah. You can put it away too.
Isn't salt water harder to boil anyways?
What?
Isn't salt water harder
Salt
to
water.
boil anyways?
Salt water is harder to boil.
Yeah.
But we're not talking salt water. Please look up. We're talking a heat exchanging fluid like ammonia. that has a low boiling point. If it has a low boiling point, then you can bring it condensed under the water, and it'll come out as a steam, so you can capture that expansion pressure.
Yeah.
Apparently not a tremendous volume of energy possible. It's very low level to begin with, so you've got very slim margins for success. This was a concept that when tried, didn't produce very much energy. Yeah?
So you condense the fluid that goes through it?
Yeah.
How do you condense it?
Well, you can just let it cool off on its own and go back to liquid. You could also pressurize it back, but then you're using a lot of energy. What?
It's a solid?
Back to a liquid. It goes from a steam back to liquid.
Oh, so
Yeah.
Are they like pipes underwater?
Yes. So this is a heat exchanger, right?
Oh my god, I know.
That's what those coils are, right? Now, this is the part where things get better, because I don't know if you noticed, the 3 historically most famous tidal power concepts have not worked out. But number 4, this has great potential. And because daddy daycare involves bath time, I will give you an analogy that's based on visualizing a fat hairy man in the bath. Clothes are on. Clothes are on.
Board shorts.
Yes, yes. I am in a bath with my clothes on, splishing, splashing. Okay? But now, no. I'm not. Watch. I want to play with a bucket. And I'm guessing all of you have some bucket experience, and some of you have some bath time experience. So first of all, if I let this go in the bathtub, it'll bob around and float for a while, right? Kind of do this. Everybody understand what I'm saying here? Because you've all played with a bucket or something. And then eventually, if I splash around enough, it might start to soak up water, and then it'll sink like that, right? Everybody with me so far? And if I want to take it out of the bath, I could go like this and let the water out. And then I got my bucket to play with again. I can play drums with it. Everybody knows how buckets work, right?
Yes.
Watch. If I go like this, what's in my bucket?
Water.
This is the water level. Look at the way I'm holding my bucket. Watch. This is the water level.
Water.
Just water. Not just water, right?
It's just water right now.
Now look. Now I have.
And you have to pull it up.
You guys are doing great. This is going somewhere. I promise. No. I'm going somewhere. I'm going somewhere. We just want to make sure we're all clear on the water level. So now.
Water.
What's in my bucket? Air. So when I let it go, what's going to happen? Right? Right? Everybody's good, right? We're doing this? Okay, watch. Water. What's in my bucket? What's in my bucket right now? So when I let it go, what's going to happen? Because I filled it up with water first. I went like this, and now it's all full of water under the water. And then I've trapped the water, right? Because there's no way for air to get in. Everybody got what I'm saying?
Yeah.
So you all know what's happening here. Now, stay with me. I got a different bucket. You all see that little air hole in the back?
Yeah. Not really. Let's say we do.
There's a little air hole.
Yeah. Tiny one?
Okay.
Why was it you're in a perfectly good bucket? Okay.
Does everybody see that hole? Okay.
Maybe.
No.
Yeah.
Thank you.
For the price of education. Now, students, get ready. Get ready. I got a different kind of bucket now. It's not a hole. Everybody see that hole?
Not really.
I see you through the hole. I know you see it because I see your eyeballs.
No, you don't.
Now, get ready. Get ready. I want you to imagine what's going to happen right there when I go like this. What's happening? Water's pushing air, right? There's air coming through the hole. And then, what's going to happen at that hole when I go like this? Right?
Yeah.
But
now,
how do you get the energy to do that? Doesn't work.
What if I'm just holding the bucket still and the water's miraculously moving on its own? Then what's happening at that hole?
You put a turbine
Right? I'm sucking air in or out, right? Because I'm not doing any work, the water is doing everything for me, right? And it's either pushing air out or sucking air in. Imagine if I had a one-way valve in two separate holes, I could have an in turbine and an out turbine, right? Everybody got this? Now, please look up. It's called an oscillating water column. It's not a bucket. It's about the size of this room. And imagine, as the sea surface goes up and down, there's a water piston in a container moving up and down, pushing air in and out through a turbine, or technically two turbines. There's an in turbine and an out turbine.
Okay.
Now all of a sudden, this is starting to sound like a real viable alternative, because please look up, this is first of all bankable. I could build like a pier with like 100 of those. And any part of the world that has significant surface agitation, all of those pistons going up are spinning one turbine, and all the pistons going down are spinning another one. You can either, please look up, combine all that electricity, or you can use plumbing to combine all the pressure and have a giant in turbine and a giant out turbine. You can do this in the middle of the ocean. We got a lot of ocean surface real estate. These add tidal habitat, because there's like shady stuff in artificial reef area. And there are parts of the world where the ocean is always doing something. Yeah.
Is the bottom part like connected to the top, or is that like completely separate scenario?
If you want a visual, this is attached to land or a pier, and the bottom of your bucket extends below the lowest chop point at the lowest tide. And so you need enough height to capture the lowest possible sea surface to the highest possible sea surface. And they're just attached sideways. So there is a continuum of water below this. The sea floor is under this. Make sense? All you're trying to capture is the surface potential.
Okay, I mean, like in the drawing, like the little columns below the sea floor.
These are two separate photographs.
Oh, okay, yeah.
This is the coastline with many piers.
Oh, okay.
Got it. Yes.
I've seen designs for these where they've used like a two-way turbine where it'll spin the same direction with air going up and down past it.
Oh. Yeah, I imagine that it's just like a, if you could isolate, well, you can't isolate the air from turbine space. I don't know how that would work.
You can make the blade
Oh,
go.
yeah, I guess so. Are we all out of time?
Yeah.
Oh, I had 2 study goals to go.
Yeah.
Save it for Monday.
You all like my demo?
Yeah.
Good. Wait.
What?